Hello, my name is Eduardo Rios, and I'll be introducing Lab 2 for Electrical Engineering, EE 120. So here I have a 2-bit mux, which basically, as you can see, gives you the output of A if the select is 0, but if the select is 1, then it gives you the output of B. You can see playing around for a little bit, that's what happens. Let me go ahead and open the next one, which is the 4-bit mux. This one's a little bit more complicated, but the same really applies. It's just now you can add hex values. So let's say it's 5 and it's still 0. You put a select of 0, you're going to get A, but you can put a select of 1, you're going to get B, change B to 4, and then you switch it back and it's 5. That's how the 4-bit mux works. After that, 4-bit mux, no, uh, the not neg what's it called? EIG. And then this basically is you get 4 bits for an input, and then you can invert it in the ones complement. So the ones complement of 4 is B, or you can also just get its negative value, which is C. Let's go, for example, you put like F. The negative, if you don't touch the negative value, nothing happens. However, if you touch its inverter, you get 0, which you can think of it as what's it called? A ones complement. But if you go one more, that's a twos complement. So when it's just the inverter by itself, it's a ones complement. When it's the -2, it goes into the twos complement. Um, let's open the next one. And pretty sure it was a display. Oh, I skipped over this one, but this is the display. Basically shows the same thing. It's just now you can see it with displays of these. So if I put in 5, you can see the displays go up and then go, let's put D down here. Same thing, if I have the select 0, it's gonna go to the top input. If it selects 1, it's gonna go to the bottom input. Same thing, I just have the displays with it. Displays, and then and add. Okay, let me go ahead and play this one. So this one is you get a hex value, let's go with 4, and a B value of 1. You can have a carry in, you can add, you can pass, as you can see here. The pass basically is just like it always goes to the A value. So for example, here, if I just keep it 0 and I just add it together, just does regular adding. Um, 4 plus 2 is obviously 6. You add a carry in, it's 7. But if you just put the pass, it just gives the pass to A, and it just A goes down. Doesn't matter if 2 changes to whatever number, it's always going to be for A, as you see right there. So yeah, that's how that one works. Let's go to the next one. The last one is the ALU, pretty sure. Just make sure. Yeah, it is. Okay. Now this one compiles all 3 of them together. It compares the add and it also compiles the net nor. Pretty sure that's how you say it. Net neg, not neg. And yeah, it just combines those two into this big thing where you have the 2 inputs. You have arithmetic, which basically is like you can do adding. Now this can be used with signed or unsigned numbers. Obviously, the system is going to treat what's it called, overflows like signed numbers and carryouts like unsigned numbers. And then obviously you have the carry-in and then the pass, which just gives a pass to A if A changes to whatever number. It's gonna be 4, doesn't change, and it doesn't change anything else. Then you have the carryout and the overflow, and then here you have the rest of them. Arithmetics, like for example, if I want to do 2 plus 4, Let me go ahead and 2 plus 4, and I press the arithmetic, and I take away the pass. It's going to give me 6. Now, if I invert 8, it's going to give me the two's complement of 2, which is just uh 2. But now it's saying -2 plus 4, which is just 2. So that's how that one works. Let me go ahead and show the GTK waveforms. Let me see. Sure. And then we're gonna go here. And then I already had them up and ready. Oh, wrong one. Wrong one. There we go. All right. Yeah. Let's go back to the beginning. So we're gonna start from the 4-bit. As you can see, this is just showing what I was saying earlier for the 4-bit mux, which is just whatever the A is, and you have the select being 0. That's what A is. That's what Y is going to be. B is if cell turns into 1, then B is going to be outputted. So that's 2-bit. This is the add, which is not the right one. 4-bit. Input. Even just go ahead and add the last two. Oh wait, no, those didn't have it. Oh yeah, it's just because it skipped over that. So yeah, after that one, we have the actual test of each of the AULs. Here it was just adding. One, you can see the first one, 1 plus 2 with no carrying is just 3. 6 plus 5 is just B. 7 plus 2 is 9, which is just A. Goes like that, goes like that. Just adds them. Second one is and, which just basically you and both of the inputs together. B plus 0 is 0. 1 plus 2, 1 ANDed with 2 is just 0. And then 1 ANDed with 7 is 1. And then 5 ANDed with A is 0. That's what that one means. Um, and okay, this is the A. So this is when pass is 1. So when pass is 0, I'm sorry, when pass is 1, this whole thing, no matter what B is, it's always just going to be that. So as you can see, A being 5, output 5, 8, 8, 3, 3, it just goes like that. Didn't matter what B was, if there was a carrying or not, it's just going to be that because it's just pass, like it passes through. The next one is the inverted AND. This is just when you combine the invert option with the AND option. And now this just flips it. So if you think it doesn't invert the whole thing, it just inverts the A part of it. So I mean, if you think about it, it really does. Because if it turned out to be 1, um if one of the inputs turns out to be 0, now the whole thing gets inverted to 0. And now if one of the inputs, if A was the one that was 0 and B was the one that was 1, and you flipped it, then it would be 1, 1, so the output would be 1. But it's not really like a full, like everything gets flipped, because there are times when, oh, for example, 1, when you go through the whole thing, it turned out to be 1, but B turned out to be 0. So the output was 0. But if you still change it and now A is inverted to 0, it's still going to be 0, 0, which is 0. So those are the cases where it gets where it doesn't really change. But as you can see here, 0, 1, output 1, D 1, output 1, and all the bottoms are 1, and then 4, just to show it. Next one is inverted A, and now this is just the two's complement of A. So as you can see, it's 5 turns into 8, 8 turns into 7, 3 turns into C, and just goes on like that. Didn't matter what B was, didn't matter if there was a carrying or not. It was just whatever A was flipped. Two's complement. And then this is the add pass. Oh, this is when it goes to show again that the pass really overcomes everything. It doesn't even matter if there is arithmetic supposed to be there. It was supposed to be 4 plus 3, and then the pass got in it too. So now it was just 4. Same thing, F, and then 2 just went down. Next one is an inverted A. So inverted A add. Oh, so this is you invert. So now you invert the A, and then that gets added to B. So the invert of one, the two's complement of one would be um F. Yeah, it would be F. So F plus two is one. And then same thing with six gets flipped, seven gets flipped, B gets flipped, five gets flipped, all that. And those are the answers right there. Zero. Um, and yeah, you just get adding them together. There was some carry out and stuff like that, and overflow in these ones because now there's actual math going into it. But then on this one, it's all the inputs, and of course, as you would expect with the pattern happening, if pass is predominantly there, then it's going to be the main thing. But now because all of them, all the inputs were selected, now even the invert of A is selected. So as you can see, F gets once two's complemented into one, A gets two complemented to eight because it's the same thing, seven to nine. Yeah, it goes double just to this one goes double just to show that it doesn't really matter what B is or what the carrying is. But yeah. That is that one, and I'm pretty sure that is the last one. But yeah, thank you for your time. This has been Lab 2.